This is a particle simulation in action. No, seriously. Well, it might not look like Boyd particles, but that's what this is. With a wave of the magic wand, it really looks like this. It's time to try out some new techniques you can use in Godot. Over the past year, I've been learning and experimenting with compute shaders in Godot. I made a bunch of particle simulations, things like particle life, Boids, and even a 2D gravity sim. You can find those projects on GitHub, and we have explainer videos for them here on the channel. Last month, I posted a video on using Texture2D to speed up these shaders. It made a big difference by keeping the image data on the GPU, and it definitely improved frame rates. But there are still a few bottlenecks left in the pipeline. In these simulations, the display texture is manually rasterized inside the compute shader. Since the particles are drawn as circles or triangles, and sometimes at fairly large sizes, the drawing loops got pretty expensive and hurt overall performance. So the question is, could we use MultiMeshInstance2D to speed this up? In this episode of the Codex, we're going to do exactly that. We'll take the Boids compute shader and speed it up using several new techniques. Let's see how this works. First, let's take a quick look at how the original shader works before any of the new changes. If you want a full walkthrough of the original version, you can check out the prior videos on the channel. It uses Godot's rendering device to execute a compute shader that simulates a bunch of void particles moving in 2D space. To do that, it uses two shader storage buffer objects to hold the input position and the velocity for each particle, and two more buffers to hold the output values for each frame. It also uses a single image buffer for the image that gets drawn to screen. Each frame, Godot runs four main steps. First is the simulation step. The shader reads each particle from the input buffers, applies the Boid movement rules, and writes the new position and velocity into the output buffers. Next, the image buffer is cleared. This just resets the pixels so we can draw a fresh image for this frame. This is the same image buffer that's connected to Texture2D, so it doesn't need to be copied back to the CPU every time we want to show it on screen. And finally, the shader loops over all of the particles again and draws each one into an image buffer, pixel by pixel. In this case, we're drawing triangles, which means looping over a lot of pixels per particle. This is one of the main bottlenecks that we're going to fix in this video. So, once those three steps are done, Godot can then display the image buffer to screen. Right before the frame finishes, we swap the input and output buffers, so the next frame can use the latest particle data as input. This involves copying the latest output particles down to the CPU and then pushing it back up as new input. And that's the whole loop. We simulate, clear, draw, and swap the buffers, and repeat that every frame. It's fast, it scales pretty well, depending on the simulation, and it produces some really awesome lifelike swarms. As a baseline, with about 10,000 Boyd particles, this original setup runs at around 130 frames per second on my older graphics card. Not bad, but we can definitely do better. Now that we know how the original shader works, let's go over the changes we're going to make. 1. We'll switch from flat storage buffers to image buffer compute textures. 2. We'll remove all of the drawing logic out of the compute shader. 3. We'll use a MultiMeshInstance2D to render the particles all at the same time. 4. We'll add a canvas item shader to draw each individual particle. 5. We'll feed our compute texture data directly into the canvas item shader. And 6. We'll change how we swap the buffers at the end of each frame. All of these will work together to greatly improve our performance. Let's break them down. The first big change is replacing the shader storage buffers with Image2D textures. Right now, each particle stores its position and its velocity in one-dimensional array buffers. Since both position and velocity are vector2 values, that's 4 unsigned floating point numbers per particle. So here's the question. Instead of storing that data in flat array buffers, can't we just use a texture? An image texture gives us pixels arranged in a 2D grid. Each pixel can contain 4 floating point channels: red, green, blue, and alpha. Together, those 4 channels form a 32-bit floating point RGBA value per pixel. But there's no rule saying that those channels have to actually represent color. Each channel is simply a floating point value, and each pixel gives us 4 of them. which means a single pixel can store all 4 values we need for one particle. Yep, that's what we'll do. This will be our compute texture. And we'll have 2 of them. Just like we had for the storage buffers, there's one for the frame's input particles and one for the frame's output particles. So instead of storing colors in this texture, we'll treat each pixel as a particle. The red and green channels will store the particle's position values, and the blue and alpha channels store the particle's velocity values. As long as we can translate which pixel maps to which particle, this works great. Our compute texture will be 256 by 256. That means it can hold just over 65,000 different particles, even though we don't necessarily want or need to use them all. Of course, this also means we'll need to update the original particle initialization code in GDScript and change the compute shader to read and write particle data from the images instead of using the original array buffers. And because we'll be operating on 2D textures instead of flat storage buffers, we'll update the shader's local size to be 16 by 16 workgroups, instead of the original 512 by 1. That change sets each workgroup to process a 2D block of pixels, which is more natural for image access, and much more efficient on the GPU. We can always adjust as needed. Interestingly, since we're using a texture 2DRD here, we can quickly show the compute image on the screen for debugging purposes. And as you saw at the start of the video, it tends to look a lot like static or noise. That's expected because the pixels aren't really storing color data anymore. Okay, now that the particle data lives in a texture, we can completely remove the drawing code from the compute shader. We'll no longer be rasterizing each particle directly in the shader, and instead we'll render everything using a MultiMeshInstance2D. MultiMeshInstance2D, along with Multimesh, is a powerful tool in Godot that's designed for drawing the same 2D mesh many times very efficiently, using GPU instancing. Under the hood, each object instance in a multi-mesh draws the same mesh. That mesh could be a quad, a triangle, or any custom set of vertices. In this simulation, we'll use a simple quad mesh. So initially, each particle would be drawn as a square, at least until later in the video. A multi-mesh is the wrapper for that quad mesh. It tells Godot how many instances of that mesh to keep track of, 1 instance per particle in our case. We'll set the multi-mesh's instance count to the number of particles in the simulation. There are a ton of other features you can use with multi-mesh, but for now we just need it to know what mesh to use, how many times that mesh should be used, and what the initial translations should be. In our case, we won't do any translations on the CPU, so we'll just set each instance to the default 0 identity. To finish up, we need to assign the configured multi-mesh to our MultiMeshInstance2D node. And now, since MultiMeshInstance2D is a canvas item node, it'll automatically handle drawing the multi-mesh instances every frame. Okay, we have the multi-mesh configured with the mesh and the instance count. And it's connected to the MultiMeshInstance2D, so it'll be drawn to screen. But at this point, nothing would be visible yet, because we still need to tell Godot where and how to draw each instance. To do that, we'll have to add a canvas item material shader. This is how we'll translate and draw each particle. To connect it up, we need to assign this material shader to the MultiMeshInstance2D. Inside this shader, 2 important things happen. First, in the vertex function, we'll read the texture data that came in from the compute shader. Each pixel in this texture represents a single particle. We'll use the instance ID to figure out which pixel to read from the compute texture. That gives us the latest position and velocity for that particle instance. Most of the sims we have on the channel allow users to zoom in and out, and pan around the image using their mouse. It's the vertex function that's responsible for handling those user settings. So scaling the quad up or down, positioning the particle, and rotating it to match the particle's direction all get handled inside the vertex function. By the time the vertex calculations are complete, each particle will be scaled and oriented correctly in world space, with its vertices moved to the correct location based on the particle's current position and movement direction, as well as translated based on the user's camera position and zoom settings. Good so far. The second important thing the material shader does is draw the particle's colors, pixel by pixel, inside the fragment function. If we stopped here, every particle would just be a square. But what if we wanted circles like in most particle sims? Or triangles like we see in Boids? To handle that, we'll add a sampler 2D uniform to the shader that acts as a transparency mask. For basic circles, a gradient texture 2D works great. It doesn't need to be large to get the effect, so I usually work with a 32 by 32 mask when testing circles. If you want to know more about using gradient texture 2D to make circles, check out a recent video on that topic. For triangles, or other more complex shapes, you have to use a custom texture to act as the transparency mask. Since Boids are commonly drawn as triangles, that's what we're going with here. Our mask shape is a very basic triangle in a 32 by 32 square image, and we'll make the top of this triangle be the front of the Boid. Once this is hooked up, the mask determines which parts of the quad are visible. So now we're drawing proper particle shapes instead of squares. Neat. Now let's connect the compute texture to our fragment shader. We have the canvas item shader that handles reading the pixel data from some image, and drawing the particle shapes based on those pixels. But we never actually assigned that image into the shader. It's easy enough. The same texture 2DRD used by the compute shader is passed directly into the material shader as a sampler 2D uniform, just like we did with the alpha mask texture earlier. That means when the compute shader updates the particle data inside the image, the rendering shader will read it directly without ever having to pull that data back to the CPU. So now our canvas item shader will look at that compute texture to get the particle data, where each pixel represents a single particle. And everything stays on the GPU every frame. Nice. At this point, the majority of the optimization work is done. In fact, we could stop here and everything should work. The compute shader is still doing the heavy lifting in the simulation, while the MultiMeshInstance2D handles the drawing of each particle using a canvas item shader. But there's still one more minor improvement we can make. Instead of manually swapping the input and output texture at the end of each frame, we can use uniform sets to toggle which images are bound to the rendering device. This simplifies the code and can shave off a bit of overhead. It's not always a huge performance win, but it's a cleaner setup and it seems like a more flexible approach, especially if you have a ton of buffers to swap each frame. In the future, I plan on updating this logic further and maybe making a video about uniform sets. But for now, this gives us a quick technique we can use across most of our sim projects. And there we go. We're now using an image buffer to store the particles instead of flat storage buffers. We're instancing and rendering particles with a MultiMeshInstance2D, and we're drawing each particle through a canvas item shader, all while keeping the particle data on the GPU. This was a pretty advanced challenge, especially since I'm just starting to dig into compute shaders and Godot's lower-level rendering features. I'm sure I'm making some mistakes, but I'm having a blast working with these. As far as performance boost goes, with this new logic, the sim handles the 10,000 Boid particles, each drawn as a triangle, running at around 250 frames per second. That's quite the improvement over the original 130 frames per second. I hope you found this useful. It's definitely a great set of features to have in your back pocket if you're needing to render tens or hundreds of thousands of particles, squares, or circles efficiently. Thanks for watching the Pathfinder's Codex. If you have questions or something on your mind, leave a comment. Drop a like for the algorithm, subscribe if you dare, and as always, never stop trying new things.